Hello everyone, and welcome to today's webinar, Vehicle Cabin Energy Management Considerations in Electric Vehicles. In this webinar, you will learn how our TAITherm software and human thermal extension can be utilized to improve vehicle designs for shorter passenger time to comfort while reducing energy consumption. My name is Chris Niva, Marketing Operations Coordinator here at Thermoanalytics and host of today's webinar. Our presenter today is Zach Edel. Zach is a senior research engineer who has been with Thermoanalytics for over 5 years. Zach is TAI's resident battery expert and chief engineer of the TAITherm battery extension. He is involved in thermoelectric and thermal CFD simulation, advanced physics modeling, algorithm development, and multi-physics coupling. He has over 13 years of research experience developing advanced physics models, performing numerical modeling, and performing experimentation and data analysis. In 2013, he received his PhD in mechanical engineering mechanics from Michigan Technological University. Throughout this presentation, you may submit questions in the questions box, and we will review them at the end. We are also recording this webinar, and we'll be sending you the link following this presentation. With that, Zach, if you are ready, you may begin.
Okay, thanks, Chris. Widespread adoption of EVs by consumers is dependent on several factors, including range satisfaction, public and private charging infrastructure, vehicle purchase price in comparison to internal combustion engine vehicles, maintenance costs, costs of exploiting the technology compared to conventional technology, reduced greenhouse gas emissions, and the existence of a reasonable thermal comfort in the operation of an EV. EV range is strongly influenced by temperature, particularly in hotter and colder climates. Colder climates are a little bit more stressing on the vehicle's range. You can see here in the map the energy consumption per mile averaged across a fleet of Nissan Leaf EVs over a year. In the north of the United States, it's quite a bit more energy consumption due to the heating factor. And on the right-hand side, you can see the influence of temperature on the energy of different battery types. And the main thing to notice here is that when the temperature of a battery goes down, it provides significantly lower energy overall. So it's important to keep the battery within a specified temperature range. When it gets too hot, the lifetime goes down. When it gets too cold, the capacity goes down. And it can also cause damage to the battery. Climate control loads cause significant range reduction both in summer and winter. In the summer, it can be anywhere between 17 and 37%. In the winter, it can be between 17 and 54%. And the amount that the range is reduced depends on the drive cycle and where you are, depends on things like how long you're driving, since there's a large energy expenditure upon the startup after a thermal soak condition. So in suburban areas, the power is lower. In urban areas, it's a little bit higher. Those might be around 50% difference. On a sloping road, the battery is exhausting a lot more energy for the traction of the vehicle, and so the overall consumption of energy due to heat is a smaller ratio. There are several active technologies for HVAC efficiency improvement. The first one is localized heating and cooling, which might be radiant panels around the person that heat up the body through radiation instead of convection with the air in the vehicle. Might be heated steering wheel, might be heated or cooled seat. Sometimes there are panels overhead. Heat pumps are a way to improve the efficiency of heating the air of the vehicle. They capture heat from the atmosphere to heat the cabin. Thermoelectric generators are something that are sometimes used in hybrid electric vehicles, at least it's under consideration and an active area of research. And these use exhaust heat to generate electricity for heating, ventilation, and air conditioning. So it's just a device that turns a temperature difference into a current, and if you put that on a hot exhaust system, it can generate electricity. There's ambient air circulation, which allows heat transfer to continue even after the engine and HVAC system have shut off. So this sort of thing might improve the amount of energy it takes for a heat up or cool down scenario, particularly a cool down scenario when the vehicle's soaking in the hot sun and the interior of the car gets a lot hotter than the outside air because of the greenhouse effect in the vehicle. So if you continuously circulate air or at some frequency, you can lower the temperature inside the vehicle to the ambient temperature, and then it requires less energy to cool the vehicle, the cabin. The simplest adaptation of an internal combustion engine HVAC system for electric vehicles is to use a resistive heater and electric refrigerant compressor for cooling. So this is just your typical HVAC system that cools your vehicle. In this case, we're talking about using the same system for an electric vehicle, and then adding a resistive heater to that system to heat up air that's coming into the cabin. So this is the easiest approach. It's also the least efficient. Some heat can be recovered from the electric motor. People are working on this. This is mostly an efficiency improvement since it's not significant enough to work on its own, but I'm sure this will be something that everybody will be looking into after these systems are well established and people have standardized parts and manufacturing for these systems. Efficiency will continue to improve by capturing heat from different components in the drivetrain, such as the inverter and the electric motor and so forth. This approach with the resistive heater and typical HVAC system causes up to 50% reduction in EV range, and it relies on a single point sensor for temperature control. And this can be very difficult for controlling the temperature of the air coming into the vehicle, since the temperature of the air around the person can be different than wherever you have a single point sensor in the vehicle. There can be gradients, and it doesn't really matter where you put it because the airflow might cause the difference to be one way or the other. It's also hard to manage the temperature of the air going out of the vehicle using a control circuit with a resistive heater because there are no limits on it. So this poses some challenges to this basic implementation of heating and cooling. So alternative options are desired. The first modification would be a positive temperature coefficient heater, or PTC heater, and this is used right now commonly in vehicles, either by itself or in addition to heat pumps, which I'll talk about in a little bit. This provides rapid noiseless warming of the cabin and windshield defrost independent of waste heat. And it's made of specialized heating discs from advanced ceramic materials, and that makes it self-regulating. So that means as the temperature of the disc goes up, the resistance also goes up, which limits the current going through the disc and the heat along with that. So this makes it so that the heater does not get too hot, and you can tune that heater to a certain level to heat the car. So the self-regulating function makes it easier to control the heat going into the cabin compared to a complicated control scenario with temperature sensors. And this makes it more efficient because there isn't any error in the control scenario. So it isn't providing more heat than necessary. This is still a resistive heating device. It uses the energy from the battery to heat up the air, and so it has poor efficiency. Just like the resistive heater, they're both resistive. All the energy comes from the battery. This one is just easier to regulate. So it can provide sufficient heat to warm the cabin, but the energy is derived from the battery, so it reduces driving range. For example, at -7 degrees Celsius, it can take 6 kilowatts of power to heat the cabin. And that's about the same amount of power that's needed to propel a small vehicle at 50 kilometers per hour. So quite a bit of energy compared to something like an internal combustion engine, which uses waste heat from an engine to heat the cabin. And this is the transient portion of the heat up at the beginning, but it also takes energy to maintain the cabin at a certain temperature. So a good alternative is a heat pump. The power consumption can be 1/3 of the PTC heating system of the same capacity. Heat pumps have been around for a long time in different applications. Some places people use them to heat their house. Not as much in the United States, but it is a well-developed technology that's finding more applications in recent years. And heating and cooling in a single refrigerant circuit can be achieved using reversible flow. And so in a regular HVAC system, the flow goes one way. You have an expansion valve in there and 2 heat exchangers and a compressor. And it makes the heat exchanger on one side cold, so it absorbs heat from the environment. And it makes the other heat exchanger hot, so it rejects heat to the environment. And typically, this would be used to absorb heat from the cabin and reject it to the atmosphere. Well, if you reverse the flow in a circuit that has an expansion valve on the opposite side, so you just switch the functioning, then it absorbs heat from the cabin and rejects heat to the atmosphere. Or the opposite, it absorbs heat from the atmosphere and rejects it to the cabin, which would be a heating function. So it's just a directional HVAC system, and it's significantly more efficient than a resistive heater. It does have certain drawbacks, however. One is in cold temperature environments, you can get frosting on the external heat exchanger. Another one is in a conventional vehicle, typically for a dehumidifying scenario, the vehicle will run the HVAC system and the heater at the same time, and that allows you to remove the moisture from the air that's coming out of the vents while allowing it to be hot enough to melt the frost on the inside of a windshield. So when you replace your HVAC system with a heat pump, it's no longer allowed to both heat and cool at the same time. So the air that's coming out of the duct has a higher humidity ratio and doesn't defrost the windshield as quickly. But people are looking into this and determining different scenarios with more than one loop in the cooling circuit and heating circuit and internal heat exchangers and things like that. And they're working on ways to get around this and dehumidify the air at the same time that it's heated for a defrost scenario. This is the dominant AC system in EVs, so it's all you need. You don't need an additional HVAC system. The disadvantage is that slow warm-up times compared with PTC heaters. So what people do is they supplement the heat pump with a PTC heater for fast response. So you add the PTC heater, it heats the air while the heat pump is warming up and the person feels warm. And then after the heat pump is warm, the PTC heater turns off and it's just the heat pump working. So this provides better cabin comfort. It's a little more expensive just in manufacturing costs, but it does allow heat pumps to perform at the same level of PTC heaters. Another active heating and cooling scenario is localized heating and cooling. And this is a fairly new technology that is being used right now in internal combustion engine vehicles. It includes things like heated steering wheels, heated seat, radiant panels. And these are very important for comfort of a passenger. One of the main things, there are a few effects that make these very attractive for passenger comfort control. One of them is that the response is very quick compared to a typical heating or cooling system in a vehicle. So for example, when you get in your car, it takes 5 minutes for the engine to heat up and provide heat from the vents. So these take maybe a minute or so to heat up. So it heats the passenger before the HVAC system is available to heat the passenger. So very quick response, small time to comfort. Another thing is they're more efficient, which isn't as big a deal in an internal combustion engine vehicle, but it's a very big deal in electric vehicles, as we'll see later on with a case study that shows a comparison. Another benefit is just that it allows you to keep segments of your body warm that are hard to maintain warm with a typical heating scenario. So a heated steering wheel means you don't have to wear gloves, and that feels good when you're driving. With the typical HVAC system in the wintertime, most times people leave their gloves on, and if they take them off, their hands aren't always comfortable. I guess it depends on how long you're driving for. But there's also scientific reasons why this is more efficient, not just in the amount of energy it takes to change the temperature of your body, but also in the way your body regulates itself and feels comfortable. And the main effect here is vasodilation, vasoconstriction. So when you're cold, your body regulates your blood flow to try to maintain your core temperature as close to the steady state value as possible, or the optimal value as possible. So when you get cold, your blood flow to your limbs is restricted, and you get less blood to your hands and feet, and sometimes like ears and things like that, so that your body can maintain its core temperature with the energy that's created with your metabolism. And that just makes them cold, because then the heat isn't flowing through your limbs, and your limbs get colder on purpose, but it feels very uncomfortable. So when you have localized heating and cooling in those areas, what it does is it increases your blood flow to those areas, and just causing your body to vasodilate from like a heated steering wheel will also increase blood flow to your feet and your head and things like that. And that allows those colder segments on your body to be warmer, which improves your overall comfort. Radiant panels are something that are being developed by OEMs right now. I think they're actually looking at putting them in conventional vehicles as well, but they'll be a lot more significant for EVs. So companies are developing them and testing them right now, and we'll see those come out more significantly when we have more EVs on the road. In order to evaluate the effectiveness of these different strategies, and also to optimize the system and tell whether or not person's going to be comfortable with a certain heating cooling scenario, and also determine what kind of heat rates you need and what kind of improvements in efficiency you get, you need a modeling scenario that can tell you how comfortable a person is. And human thermal comfort is defined as that condition of the mind that expresses satisfaction with the thermal environment. So it's very subjective. It's basically just a physically justifiable representation of how a person's comfort responds to certain stimuli and temperatures and gradients. And it's calibrated using data that's taken from people sitting in a controlled temperature environment with a certain temperature change. So it's really just a matter of how people feel, and they report how they feel, and then those feelings go into a model, and the model takes into consideration where they started and how hot or cold they're getting and how it feels on their skin. And that is how we're allowed to evaluate what a person will feel in a modeling scenario. An equivalent temperature is not enough. So in this scenario, there's a 45-minute test here with people in a controlled temperature environment. Starts out very cold, warms up, and then cools down. And test subjects reported feeling warm from the cold environment. They reported feeling warm while the temperature was only 15 degrees Celsius. So it felt good to have that heat after a very cold environment. Then after the temperature got got a lot warmer, they were reported feeling cool when the temperature was 22 degrees Celsius. And this is typical because they're already warm, and then the reduction in temperature feels good to them. So you can see there's quite a bit of difference here in how they're feeling with regards to the temperature of the room. And you can kind of think of this like when you come out of the cold, it feels good to be in a warm environment, or when you come out of the warm, it feels good to be in a cold environment. And those temperatures are significantly different than what you would regulate that temperature to be if you were sitting there the whole time. So the comfort depends on gradients, and it requires a model to predict how someone is feeling independent of equivalent temperature, or based on it, but considering more factors. And for this, we use the TAITherm human thermal extension. And the human thermal model is multiple body segments with different tissue types per segment, and multiple layers with different tissue types as you go in or out of the person. Some of the model inputs are clothing thermal properties, activity level, meaning how much a person is working, or what they were doing before they got into a vehicle. And then there's the anatomical description, which determines like how big someone is and whether they're male or female, and those kinds of things. Then the model outputs are clothing and skin temperatures, core body temperature, interior tissue and blood pool temperature, and then thermal sensation and comfort. And it depends on the scenario which one is the most significant. Sometimes when one doesn't really describe what you expect to be going on, another one is relevant. But typically the thermal sensation and comfort are your biggest factors that you're interested in, particularly comfort. And the model uses a thermoregulation model in it to describe heat transfer with the environment, metabolic heating, or how hot you're getting from how active you're being, shivering, which increases the heat rate in your body because of the activity, sweating, which cools your body from latent heat transfer. When that liquid on your skin evaporates to the environment, it increases heat transfer and cools the body. And then also vasomotion, which describes how the heat is carried around the body from blood flow. And thermal sensation and comfort are generally the metrics that are used to evaluate the person's comfort. Sensation is how hot or cold something is perceived to feel, and comfort is whether the sensation makes the person feel good or bad. So sensation is from -4 to +4. You generally want something around 0, which is neutral, not hot or cold. Comfort is also a scale from -4 to +4, but those are anywhere from very uncomfortable to just comfortable to very comfortable. So in that case, you want the highest number possible. And some of the design objectives of common cabin studies are reducing the energy consumption, balancing occupant comfort and vehicle range, shortening the time to comfort, maintaining the comfort, and that includes things like improving and studying localized heating comfort, localized heating and cooling comfort, transient environments, and autonomous seating design, which might involve people moving their seats in autonomous vehicles because they no longer have to be driving and can rotate into a different position or something. And then the way the HVAC affects the person might be different. And so that's an upcoming scenario that people are looking into. There are different methods available for simulating cabin comfort. The simplest one is a standalone fluid node in the cabin. Then you can add multiple fluid nodes to have different temperatures at different portions and advection between the fluid nodes. You can do a 1D coupling, which might be anywhere from 20 to 100 K cells. And then you can do TAITherm to CFD coupling, which is millions of cells. And then there's TAITherm mannequin coupling, which actually uses a full-size mannequin with sensors on it in the cabin of the vehicle, and that measures the person's local sensation in the cabin over all the segments, And it also depends on the mannequin temperature, so that's regulated by TAITherm. And these two are coupled together so that the metabolic response of the person can be actually applied to the mannequin, and then the mannequin reads the thermal sensation from the cabin as it's being heated or cooled, and then TAITherm calculates the comfort based on that. So these different methods have different degrees of accuracy, and the more accuracy you require, the more computational effort it's going to require, and the more time it takes. So there's a trade-off, and which one you should choose just depends on your constraints and what you're really interested in. We did a case study to show the difference when we add localized heating to an electric vehicle. And so energy use is optimized using CoTherm, which is a CAE process automation software that's developed by TAI. And we consider 3 cases with variable power to the heating sources. One is HVAC only with foot heating. One is HVAC only with panel heating. And then one is HVAC plus localized heating. And the localized heating includes radiant panels, the seat heater, and a steering wheel heater. The different tools that are used here or could be used here are TAITherm, which is our 3D thermal solver, CoTherm, which is our process automation software, the human thermal comfort module, which predicts how a passenger feels, and then the battery extension, which might predict how far the vehicle will drive at a given temperature and energy usage rate. So that would give you range. For this study, we're just looking at the first 3 because we're interested in the amount of energy that's consumed and not necessarily the actual number of miles that a person will drive and how that's affected by the temperature of the battery. So we use an optimization process in CoTherm that determines the best variable values. The inputs are the variable values with bounds, the cost function, which tells you how good or bad you're doing for a given set of variables, the optimization method, and stopping criteria. And from this, you get optimized variables that minimize the cost function based on your user requirements. Here's our process. First thing we do is import boundary conditions and run the thermal model. Then we read time to comfort from the Berkeley comfort text file, compute the power used during the run, and calculate the cost function. And some of our inputs are the panel power for HVAC, the floor power for HVAC, the roof radiant panel power, console radiant panel power, seat back power, seat bottom power, and steering wheel power. And the cost function is the sum of all these plus a penalty based on the distance from the target. The target here is a few minutes to comfort to just comfortable. So we're looking at the amount of time that it takes to heat up the person to where they're just comfortable in like 5 minutes. And we're adjusting the powers of all of our different heating capabilities to do that, and then evaluating based on the maximum power how good or bad we're doing. The optimization method is global, and the stopping criteria is 300 iterations. This shows thermal results as an animation. So you can see here, when the HVAC's on the floor, the person's feet are warmer. When it's on the panel, the person's feet appear to be cold. You can also see how the head is doing. When it's on the panel, the head is warmer. And one of the most important things to take here is when we have the heated surfaces mode, you can see the temperature of the surfaces around the passenger don't get as hot, but the passenger is just as comfortable in that 5-minute duration. So you can automatically see here that the heated surfaces mode is a more efficient way to maintain comfort. And when we compare the energy for these 3 scenarios, when HVAC is directed at the upper body, we're looking at about 3.3 kilowatts. When it's HVAC directed at upper body and legs, it's about 3.3 kilowatts. And then when you have HVAC and heated panels, the total drops to about 0.9 kilowatts. So we're looking at less than a third of the total energy when we to maintain the same comfort using these heated panels, and so HVAC is 600 watts and the other ones are about 340 watts. So the majority of the heat is still in HVAC, but you can see that 1/3 of the total heat that's required here is these localized heating features, and that reduces the overall amount of energy that's expended by about a third, or to a third, so it reduces it by 2/3. Then you can look at overall comfort here. When it's directed at the upper body, the comfort drops off after 5 minutes. When it's directed at the upper body and legs, it maintains the comfort but does start to drop slightly. This could be adjusted by adjusting the heat rate and the airflow and so forth. But when you look at the overall comfort with the localized heating and cooling, you can see it's very stable. So we have less to worry about in terms of control, and it's going to maintain the passenger comfort throughout the duration of driving. In conclusion, local comfort can greatly increase overall comfort. It provides a more stable comfort over time and uses much less energy. And if we convert the amount of energy that was required during 10 minutes into the amount of capacity that's taken out of the battery, for HVAC only, we're looking at about 555 watt hours. For HVAC plus heated surfaces, we're looking at about 157 watt hours. So less than a third of the amount of energy coming out of the battery means that if a vehicle were to have a 200-mile range with HVAC, might have a 300-mile range with localized heating and cooling, which is very significant, not only in how far you can drive, but also in the amount of infrastructure that's required to support electric vehicles, how far apart you have to place charging stations, and also how often a person has to stop to recharge, which is an inconvenience. So possible next steps to improve this analysis are adding fidelity to the fluid node model to better represent different HVAC modes and settings, adding additional HVAC settings to include recirculation. So instead of continuously heating the cold air from outside, you're going to reheat the air that's coming from the cabin. Explore additional variables for optimization runs like glass properties, panel location and size, and things like that. You can explore different cost functions. So in this case, we were only worried about the amount of energy it took to maintain or to reach just comfortable in 5 minutes. You can also look at sustaining comfort or different times to comfort, things like that. And then you can explore different ways to apply heat to the model. So in this case, we used flat heat rates. You could also, if you think about when you get in your car, when the air is cold, you turn the flow down and then the air warms up and you turn the flow up. So you've got variable temperature of the vent air and also variable velocity. And for the localized heating, generally people will turn their seat heater up on high when they first get into the vehicle, and then after they get warm, they turn that down. So there are some different ways you could apply the heat to make this more representative of what a person will actually do. So thank you for attending. I've included my office phone and email here. You can also go to our website, www.thermoanalytics.com, and I'm sure you'll find more information on our modeling capabilities and what products we provide and services. And I'm sure this webinar will also be included on our website so that you can share it with your colleagues.
All right, thank you, Zach. So we have some time to review some questions that came in. Let's see, can the optimizer consider multiple design objectives at the same time?
Yeah, you can include different design objectives in your cost function by adding penalties or scaling factors to your individual terms in the cost function, which is defined by the user. So if you want to balance different variable values, you can have different terms in the cost function with different equation types, forms, like products or exponential or logarithmic or something like that, to control how the cost function is computed based on your inputs, and then the value of the cost function is going to determine when the optimizer stops changing variable values.
Okay. Can you model the frosting of the external heat exchanger in a heat pump?
Yeah, we do have a humidity model now that can model defrosting and frosting of different things. So that could be the heat exchanger on the outside, or it could be the defrosting of the windshield, which is a more typical thing that people are considering right now. And look at phase change on those surfaces. So that could be used in conjunction with other tools to evaluate what you need to do to make the system work.
Okay. Can you add or change clothing types to include gloves and hats?
Yeah, you can make the clothing types however you want. And sometimes that's important for evaluating overall comfort, because it's typically dependent on the minimum, the comfort in the minimum segments. So you want your model to be representative of what people are actually doing, and you could put gloves on people, or in the case of localized heating, they'll take their gloves off if the steering wheel's warm. Same thing with overhead panel heaters. Typically people wear hats until the vehicle gets warm, then they might take their hat off, and that might happen at an earlier time with an overhead heater. So those can be some important factors.
Okay, one more here. Can we couple with 1D tools for heating control scenarios?
Yeah, with CoTherm, you can couple with a lot of different tools. We have some baked in. I think with GT Suite, we have a set of tools that are baked in, but in general, we have some very generic coupling interfaces that allow you to couple with a lot of different tools. We've coupled with Simulink before. You can do custom scripting with Python, all sorts of things to include 1D controls in your model.
Okay, looks like that's it for questions. That will complete today's webinar. We appreciate you all attending, and thank you, Zach, for your presentation. You'll receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. If you have any other questions, please do not hesitate to reach out to us. And thank you for attending.